Okay, so good afternoon, everyone. My name is Francesco Petruccione, and I'm the interim director of NITheCS. Welcome to our NITheCS Colloquium. And today we are very happy to have as a speaker a former NITheP, you see NITheP over there, NITheP postdoc, yeah, who spent several years with us at the Stellenbosch node of what was then NITheP. Yeah, and today Laure is a visiting scientist at the ICTP in Trieste, in Italy, where she's been staying, I think, for around 10 years now. Yeah. So after she left South Africa, she moved to Italy, but she's also involved still with AIMS. She's an AIMS community member, and she's also a member of the, I'm not sure what the ICMPA acronym stands for. Yeah, in Benin. Yeah, it's a UNESCO-Chair in Benin. Yeah. So we are really very happy, Laure, that we reconnected after so many years, and it's a pleasure to have you with us this afternoon. So if you would like to start sharing to your screen, you're welcome to get ready for your presentation. And as usual, Professor Sinaisky kindly agreed to moderate the question session after the talk. So please, if you have questions, pose them in the Q&A facility, which is on the right-hand side of the bottom bar in your Zoom screen. So Laure, please, you're most welcome to start your presentation.
Thank you very much. And let me start by sharing my presentation.
Perfect.
So thank you very much. And let me say first, good afternoon, everyone, or good morning, everyone, depending on where you are. And welcome to the colloquium with the title, The Beauty of Quantum Mechanics. So I would like to start first with some acknowledgement. I would like to thank the National Institute for Theoretical and Computational Science, NITheCS, for the invitation to give a talk. And I'm really happy after many years I left to be back. It's virtually, but it's still good. And I would like to thank Professor Francesco Petruccione, Interim Director of NITheCS, that has just introduced me. I would like to thank Mrs. Renee Kotze, Communication Officer at NITheCS, with whom I've been discussing the last days for the colloquium arrangement. As Professor Francesco Petruccione said, I am a former NITheP postdoc, and NITheP stands for the National Institute for Theoretical Physics, and NITheCS is the transformation of NITHEC. And I would, as a former postdoc at NITheP, I would like to say also welcome to NITheCS, and I'm really glad I can be talking today. So I spent 2 years as a postdoc at the Stellenbosch node, and today I'm thinking of all former members of NITheP when I was there, and in particular, I'm grateful to Professor Scholes, that was the director at NITheP when I was there. Also Professor Hendrik Geyer, that was the director of STIAS, because I used to be in the campus of STIAS. And I cannot say all of these things without saying also a big thank and goes to Professor Fritz Hahn. That was when I was there, he was the former director at AIMS. And before joining NITheP, I spent 2 years at AIMS under the direction of Fritz. And Professor Hahn was the first one to tell me about NITheP when it was a project in 2006. So I'm glad I'm connected, and today I can give a talk. And memories of NITheP, this is the Chris Engelberg Summer School, that was 2009. And another Chris Engelberg Summer School in 2010. These are very beautiful memories to say also that I'm very happy of the time I spent there. So let me start now with the outline of my presentation. I will start by saying about quantum physics, from quantum physics to quantum mechanics, then quantization procedure in physics, then coherent state, then non-emission quantum mechanics, non-commutative quantum mechanics, quantum Newtonian cosmology, quantum information theory, and I would like to end with what makes quantum mechanics beautiful, why quantum mechanics is beautiful. So you have to be passionate to listen till the end, and I make you travel in a journey from one research topic to another that are all my interests in research. So let me start from quantum physics to quantum mechanics. Why I wanted to say about quantum mechanics and quantum physics, because for physicists it's different, and I will say why. Classical physics describes physics at the macroscopic level, and most usually classical physics refers to pre-1900 physics. It's still used in modern science and technology. Towards the end of the 19th century, scientists discovered phenomena in the macro, means large, and micro, means small, world that classified physics could not explain. In the early 1900s, physicists, through experiment, discovered that atoms and their components follow different laws than the law of classical mechanics, which is the mathematical laws governing the movement and forces among ordinary objects. To make the difference with classical mechanics, physicists called the new field quantum theory or quantum physics. At the beginning, physicists developed quantum laws which were heavily verbal rather than highly mathematical. In the 1920s, physicists developed mathematical laws which describe quantum behavior. In particular, Schrödinger and Heisenberg developed the key mathematical laws governing quantum particles. At this point, physicists began calling the new field quantum mechanics on the model phrase of classical mechanics. The term quantum mechanics means the same thing as the quantum physics. The term mechanics emphasized doing calculations. The distinction between quantum mechanics and quantum physics is observed by physicists and not necessarily by non-physical, non-professional people in physics. Quantum mechanics is a fundamental theory in physics which describes nature at the smaller scale of atomic and subatomic particles. Now, my first station is quantization procedure in physics. In physics, quantization is generally understood as a correspondence between a classical and a quantum theory. The question is, how can we construct a quantum theory if a classical system is given? If we consider the quantum theory to be a more fundamental theory and classical mechanics to be only approximatively correct, the very concept of quantization seems pointless or appear to be ill-founded since it attempts to construct a correct theory from a theory which is only approximatively correct. For instance, there is the phenomenon of classical anomaly in the sense that if the quantization of some models gives the necessary quantum system, it may turn out that not all the quantum symmetry properties of the system are automatically reflected at the classical level. There are quantum systems for which no classical counterpart exists. For example, the helium superfluidity, and some broad class of such systems can be found in the literature. Quantum mechanics, like other physical theories, means classical mechanics, electrodynamics, relativity, thermodynamics, cannot be derived. The law of quantum mechanics expressed in mathematical form are the result of deep physical intuition, as indeed are all other physical theories, where validity can only be checked experimentally. From this point of view, quantization is not a method for deriving quantum mechanics. Rather, is a way to understand the deeper physical reality which underlies the structure of both classical and quantum mechanics, and which unifies the two from geometrical perspectives. It's conceptually very difficult to describe a quantum theory from scratch without the help of a reference classical theory. The similarity between classical and quantum physics is large enough to make quantization a worldwide approach. Originally, Dirac introduced the canonical quantization in his 1926 doctoral thesis titled The Method of Classical Analogy for Quantization. The canonical quantization or correspondence principle is an attempt to take a classical theory described by the phase space variable, let's say PQ, and the Hamiltonian to define or construct its corresponding quantum theory. Let's say we have QI/PI, a canonical position and momenta for a classical system. Then the quantized counterpart will be operators. Usually operators are expressed with hat on notated label with hats. And then the realization is that the position operators realized by multiplication with the I component, and the momenta realized as derivation, partial derivation with respect to the I. And some of publication related to quantization are the following. First, I want to mention that the Dirac's is on the canonical quantization procedure, but there's also the Dirac constraint quantization procedure that I used for my doctorate work. And my doctorate has been supervised by Professor Laure Gouba and Noncommutative, and I am grateful to them, and I would like to say here also thank. Then I used this method of Dirac constraint quantization procedure to study the Yukawa model in one space, one time dimensions. That was in 2018. Then I also used the same method to work on the Dirac method for to work on the two-dimensional damped harmonic oscillator in the extended phase space. That was again 2018. And there are more, of course, is not only the canonical quantization procedure that there are other more quantization procedure. And with Professor Andrea Finks and collaborator, we have a paper on the Riemann quantization for non-emission system. And I also, in 2019, I was interested in understanding beyond coherent state quantization, and beyond coherent state quantization is about integral quantization, and this procedure I would refer to the work of Professor Jean-Pierre Gazo and collaborators. And recently, during lockdown, I've been interested in affine quantization on the half-line, and affine quantization is due to Professor John Cloud, that I get a chance being in touch for discussion to see what we do beyond affine quantization. Now, next session, I want to talk about coherent state. In physics, especially in quantum mechanics, a coherent state is the specific quantum state of a quantum harmonic oscillator, often described as a state which has dynamics most closely resembling the oscillator behavior of a classical harmonic oscillator. The first example of what is now called coherent state was discovered by Schrödinger, as he was interested in studying quantum states which restore the classical behavior of the position operator of a quantum system in the Heisenberg picture. That was in 1926. He considered an operator like in equation 2 together with a quantum Hamiltonian system. And Schrödinger understood by classical behavior that the expected value or average value Q bar of the position operator that is capital T Q in the desired state would obey the classical equation of motion. Schrödinger discovered the first example of coherent state pertaining to the harmonic oscillator, known universally to physicists, and the prototype of every integrable model. For example, the state that Schrödinger has found as parameterized by complex number Z, and the mean value is follow equation 4. Even though the uncertainty relation had yet to be discovered at that time, from viewpoint that most closely resemble the modern minimum uncertainty method, Schrödinger had discovered the coherent state. The notion of coherent state is rooted in quantum physics and its relation to classical physics. The word coherent derives from the current language of quantum optics. Coherent radiation source emitting coherently. The term coherent was introduced by Glauber in 1963 in the field of quantum optics, and it is for a special property in quantum optics that the name coherent state was originally chosen. The importance of coherent state became widely recognized during the 1960s due to the work of Glauber, Clauder, and Sudarshan. And we have also some publication related to coherent state. Some of the work is about time-dependent Q-deformed coherent state for generalized uncertainty relations. And that was with Professor Andreas Frings and collaborators that were at that time students and postdocs. And I visited them in London. So later myself, I extended this work by looking at 2 dimensions, and that work was about the time-dependent Q-deformed B coherent state for generalized uncertainty relation. Then with Professor Dawood from Morocco, that is associated at ICTP. While visiting ICTP, we have worked on generalized Grassmann variable for quantum Kitt system and Baruch-Girard-Zero coherent state for SUR+1 algebras. Then a work with Dr. Latevi, that at that time he was a student in Benin of Professor Abousevu. We work on the Lewis-Riesenfeld quantization and SU11 coherent state for 2D damped harmonic oscillator. And I also reconsider beyond coherent state quantization that has been published in 2009. And recently, just on June, this June, with Dr. Isiaka Aremwa from University of Lomé in Togo, we have been working on coherent state for the system of an electron moving on plane. It's now in the review. So next session, I want to talk about non-emission quantum mechanics. Non-emission quantum mechanics is the study of quantum mechanical Hamiltonian that are not emission. Physicists Carl Bender and Professor Stefan Bocher published in 1998 in Physics Review Letters a paper in quantum mechanics about real spectra in non-emission Hamiltonian having PT symmetry. In this paper, the authors found non-emission Hamiltonian endowed with an unbroken PT symmetry also may possess real spectrum. PT symmetry means invariance with respect to the simultaneous action of the parity inversion and time reversal symmetry operators. Professor Ali Mustafa Zadeh introduced in 2002 the notion of pseudo-hermiticity and showed that every Hamiltonian with a real spectrum is pseudo-emission. He found that all the PT symmetric and non-emission Hamiltonian belong to the class of pseudo-emission Hamiltonian. The prefix pseudo means usually to mark something that superficially appears to be one thing, but is something else, just to explain probably where pseudo derived. And some of our publications related to non-emission quantum mechanics, string from position-dependent non-commutativity, that was a joint work with Professor Scholes and Andrea Frings. Minimal areas from Q-deform oscillator algebra, that is a joint work with Professor Bijan Bakshi from India and Professor Andreas Frings. PT symmetric non-commutative space with minimal volume uncertainty relation, a joint work with Dr. Sandeep Dey from India, that was at that time former PhD student of Professor Andreas Frings. And mild quantization for non-emission system. In fact, all publications related to non-emission quantum mechanics are to see with collaboration with Professor Andreas Fink, that is one of the leading experts in the field. In fact, I started doing that when he visited NITheP in 2010 and get involved to our activities of research. Now, this station is about non-commutative quantum mechanics. Okay? And I work over, let's say, 10 years on non-commutative quantum mechanics. So one of the problems in the 1930s was how to resolve infinities in the newly introduced quantum field theory. The idea of extending non-commutativity to the coordinate as a possible way of removing the infinite quantities appearing in field theories was suggested by Heisenberg. The first concrete paper about non-commutativity has been published by Snyder in 1947. The renormalization theory took over the ideas about non-commutative coordinates because the normalization theory, I think, was powerful in the 1950s, and then it took over about these ideas of Heisenberg. And between 1980s and 1990s, Alan Cohn, French mathematician, developed a non-commutative geometry that has been very successful in attracting the attention of particle physicists and string theorists. The simplest non-commutativity one can postulate is that the space-time coordinate satisfy the commutation relation xi xj is I theta ij, where theta ij is a constant antisymmetric tensor of dimension length square. But there are problems. Let's see the consequence of space-time coordinate non-commutativities. The action for quantum field theory on non-commutative space is obtained from a usual quantum field theory through replacing the field product by Moyle star product. An uncertainty relation between position measurement will a priori lead to a non-local theory. The presence of the constant theta Ig violates Lorentz invariance in the situation where the dimension of spacetime is greater than 2. There is a persistence of the ultraviolet divergences in non-commutative quantum field theory. The time-space non-commutativity lead to violation of unitarity and causality. Despite the consequences featured, there are consequences are not nice, but there are still strong motivation in studying non-commutative spacetime. There is a long-held belief that in quantum theories, including gravity, spacetime must change its nature at distance comparable to the Planck scale. One might also study non-commutative theories as interesting analogs of theories or more direct interests such as Yang-Mills theory. Non-commutative field theory is also known to appear naturally in condensed matter theory. For instance, the theory of electrons in a magnetic field projected to the lowest Landau level, which is naturally thought as a non-commutative Chern-Simons theory. In non-commutative quantum mechanics, with commutative time evolution, we do not encounter the problem that may occur in non-commutative quantum field theory. So it's well suited as a toy model for the introduction of non-commuting coordinate. That's why I was also interested in non-commutative quantum mechanics and not non-commutative field theory, because there is a lot of problems. So quantum theory has been reformulated around 1925 with the fundamental Heisenberg commutation relation of phase-space algebra and the associated uncertainty principles. One of the fundamental features is to deal with operators that do not commute. More precisely, the commutation relation between positions and momenta. So the terminology non-commutative quantum mechanics expresses that the position operators do not commute. More generally, one can consider the situation where the commutators of coordinate and momenta are non-canonical. So some publication related to non-commutative quantum mechanics. There is this beautiful paper of us with Professor Scholes and collaborators that were at that time his students. It was about interpretation and application of non-commutative quantum mechanics. Is well ranked in terms of citation, and I'm happy about that. So with Professor Scholes, we have also worked on the uniqueness of the unitary representation of the non-commutative Heisenberg veil. Also, we have worked on non-commutative quantum mechanics, the perspective on space, on structures and spatial extent. And also there is this joint work with Professor Flynn on string from position dependent and non-commutativity. So those work have been done at NITheP when I was a postdoc within the research group of Professor Scholes. In fact, a non-commutative quantum mechanics has, for me, has started at Stellenbosch. And there are other more publications. The moment I am at Trieste, I used to collaborate with Rudo Boskovic in Zagreb. And with the group there, we worked on some formulation of Moyan and Voss product and its physical interpretation. That was a collaboration with Professor Melianak at the Theoretical Physics Division of the Rudo Boskovic Institute, Zagreb in Croatia. So Croatia doesn't border with Italy, but it's for me 4 hours by bus to do the trip to Trieste, Zagreb. So I did collaborate for, I don't know, till 2013. So also with Professor Benanti from University of Trieste, we studies the classical limits of quantum mechanics on a non-commutative configuration space. And I did a review, a comparative review of 4 formulations of non-commutative quantum mechanics, because in the literature there are a lot of work on non-commutative quantum mechanics, but formulation are usually not the same. But I pick up when wanting to do a review and I study many articles, I pick up, I can cast in 4 groups, then I pick up 4 formulations. And also with Dr. Lawson, when he was a student, we study a 2-dimensional non-commutative gravitational quantum. So the next station is about Newtonian quantum cosmology. Okay. So the application of quantum theory to the description of the universe as a whole is called quantum cosmology. One possible motivation for studying quantum cosmology comes from quantum gravity. Cosmological models are a simple example to which quantum gravity ideas may be applied. A second motivation concerns initial conditions in cosmology. In quantum cosmology, the universe is treated as a wave function instead of a classical space-time. General relativity describes the observed universe very well. However, it's a complicated theory and often is difficult to find solution. The Newtonian theory, on the other hand, is in many ways far simpler and is very often able to satisfactorily model the universe. The Newtonian cosmology began with the work of Sequeira and Mile in 1934, in which simple isotropic and homogeneous universe were studied. And the 2 assumptions fit well with the observed universe, namely the expanding universe free of rotation and chairs. And a quantum Newtonian cosmology was proposed by Friedman and collaborators in 2004. And it's possible to construct a wave function for Newtonian cosmology in the framework of non-relativistic quantum mechanics. And this year, on I think it was in April, I was interested revisiting the quantum Newtonian cosmology, but using using affine quantization procedure. In fact, this was the motivation. And in this paper, we consider a small spherical portion of the universe where Newton's, there is a little mistake here, Newton's theory applies, and the behavior of this portion may reflect the evolution of the universe. So I used affine quantization because the length scale is positive, and to do quantization, I find suitable working on the half line and then using affine quantization procedures. The solution I get of the time-independent Schrödinger equation is of type biconfluent Earn function, where the 2 first parameters are fixed to 2 and 0 respectively. But one has to see or to know about these special functions, then one see how it works. And the Newtonian approach is most simple from the conceptual and mathematical point of views. However, it meets also problems and criticism. There is no time, otherwise I would have shown some of the very strong criticism about the Newtonian approach for cosmology. Now, my last station is about quantum information theory. Okay. Classical information theory is the mathematical theory of information processing tasks such as storage and transmission of information. Quantum information theory is the study of how such tasks can be accomplished using quantum mechanical systems. Quantum information theory brings together ideas from classical information theory, quantum mechanics, and computer science. Quantum information theory deals with how quantum mechanical properties of physical systems can be exploited to achieve efficient storage and transmission of information. The underlying quantum mechanics leads to important differences between quantum and classical information theory. Now, I have some motivation of why I am interested in quantum information theory, and you will see here the title I put, Quantum Information Theory Unmatched, because it's what I'm leading to. It's my interest now, and there are some motivation because with Professor Benatti from University of Trieste, we studied another paper that was the interpretation of the classical limits of quantum mechanics on a non-commutative configuration space. And after this work, Professor Benatti told me it would be good that we study entanglement. But at that moment, I was still having the mind in non-commutative quantum mechanics. Also, I was thinking I want to write a review, so I have to study certain. I told him we'll see later, but we haven't started yet. Then with Professor Daoud from Morocco, we wrote in 2017 about generalized Grassmann variable for quantum kit system and Baruch-Girardot coherent state for SUR+1 algebra. Their ideas already about qubit kits were emerging, and this is also some premise for quantum information theory stuff. And also with Dr. Nabil Abibala, that is also collaborating with Professor Daoud. When he visited ICTP, I think in 2018, we start discussing on quantum discord. And I think it was my first step getting to understand entanglement and quantum discord. And now there is a initiation of collaboration, because a collaboration discussed with Professor Mohamed Daoud. Daoud is from Ibn Tufal University in Kenya, from Morocco. And for instance, we have an interest in quantum metrology. Okay, and also I attended there is an annual meeting of the national group in Morocco for quantum information that leads I would say is a network that's lead. One of the leading members is Professor Daoud, and in March I have followed this annual meeting that is online due to the pandemic situation, and from that I am regularly invited for the group seminars and meetings, and I always follow whenever I have time. So it's something that is really initiated and going on. Also, a collaboration is recently discussed with Professor Dagmar Gross. She is from University of Düsseldorf in Germany. And with Professor Gross, we are interested in quantum entanglement and quantum discord. But of course, the initiative of research in quantum information theory and the related collaboration needs funding. So if there is no funding, it will be difficult to pursue all those nice collaboration. Now I've made you go through a journey that is travel through my research topics where if you see keywords and all my research topic is quantum mechanics. And of course, that make me feel to talk about the beauty of quantum mechanics because it's because quantum mechanics is beautiful that I'm always in various topics but related to quantum mechanics. Now, this is a one thing, but now I want to show you, that is the last point, about what makes quantum mechanics beautiful. Let's follow that. So, Edward Witten, okay, that is a field medal 1990, says, quantum mechanics brought an unexpected fuzziness into physics because of quantum uncertainty, the Heisenberg uncertainty principles. String theory does so again because a point particle is replaced by a string which is more spread out. Okay, this is what you think quantum mechanics and related to string theory. Michio Kaku, that is an American theoretical physicist, futurist, and popularizer of science, says that common sense has no place in quantum mechanics. And Stephen Hawking, English theoretical physicist, cosmologist, says the following: although quantum mechanics has been around for nearly 70 years, it is still not generally understood or appreciated, even by those that use it to do calculations. And Steven Weinberg, Nobel Prize, 1979, Nobel Prize in Physics, 1979, says, quantum field theory, which was born just 50 years ago from the marriage of quantum mechanics with relativity, is a beautiful but not very robust child. C. Roger Penrose, Nobel Prize in Physics in 2020, says, quantum mechanics makes absolutely no sense. And Richard Philip Feynman, American theoretical physicist, Nobel Prize 1965, says, I think I can safely say that nobody understands quantum mechanics. And John Archibald Wheeler, American physicist, says, nothing is more important about quantum physics than this. It has destroyed the concept of the world as sitting out of there. The universe afterwards will never be the same. And Paul Dirac, English theoretical physicist, said, quantum mechanics has explained all chemistry and most of physics. And when Heisenberg, German theoretical physicist, Nobel Prize 1932 for the creation of quantum mechanics, says, the basic idea is to solve all fundamental difficulties onto the neutron and to do quantum mechanics in the nucleus. Schrödinger, Austrian Irish physicist, Nobel Prize 1933 says, the mathematical framework of quantum theory has passed countless successful tests and is now universally accepted as a consistent and accurate description of all atomic phenomena. Niels Bohr, Danish physicist, Nobel Prize 1922 says, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. And Einstein, Nobel Prize 1921, Albert Einstein says, quantum mechanics is certainly imposing, but an inner voice tells me that this is not yet the real thing. The theory says a lot, but does not bring us any closer to the secret of the old one. At any rate, I'm convinced that he's not playing at dice. So this is the end of my talk, and thank you for your attention, and thank you for listening.
Thank you very much, Laura, for a very nice historical overview of the beauty of quantum mechanics. Thank you very much. It was very entertaining and informative. Thank you so much. Ilya, will you please guide us through the Q&A session?
Of course. So far, there is no questions. I don't see any questions, so people are welcome to, because we're not so many, so people can raise their hand, and essentially, yes, we can give them a right to ask the question. But also, maybe I can start with a question. Because, you know,
yes.
On some stage in your talk, you mentioned PT-symmetric quantum mechanics.
Yeah.
And as within the kind of generic framework of non-Hermitian quantum mechanics.
Yeah.
And recently, I think, I don't know, are you aware of not? Recently, Barry Sanders, together with co-authors, issued they made a kind of paper where they have demonstrated that essentially for the PT-symmetric case, like for each PT-symmetric Hamiltonian, you can always identify the inner product with respect to this, which you are acting like with a normal Hermitian quantum mechanics, and essentially like extension to the PT symmetry doesn't give you any kind of computational or any other advantage. Do you know if there is a similar works for the other non-Hermitian extension or non-Hermitian extension, in the sense like, okay, you can construct can we learn something?
You mean by constructing like the Dyson map?
I don't know, whatever way. Like, I mean, like,
yeah, there is because in one of our work we have non-Hermitian operators, but then we have constructed the Dyson map, and with Dyson and mapping with that we got Hermitian operator, and we reformulate to have hermiticity. And I know well about this paper that is well known. I think it's a paper from Professor Fritz Hahn, Professor Hendrik Geyer, and Scholes is about that, but is about constructing a map that I call Dyson map, or mapping the non-Hermitian operator to Hermitian operators, and reconstructing, reformulating the theory to work with. I'm not sure if I answered the question. Also, I think I don't hear very well.
Oh, okay. I mean, you partially answered, and I think there's somebody who wants to ask the question. I think I will get the chance to a person.
I think there is a raised hand, Ilya.
Yes, yeah.
Hello.
Yeah, you're welcome to ask your question.
Hi, how are you?
Fine. You sound Daphne.
Yes, yes.
Oh,
yes.
Daphne, how are you?
I'm good, I'm good. I saw the email about your talk.
Yes.
And you know me, I really like you, I like your work. And I said I'm gonna attend even if I don't understand much about your physics, but I just wanted to be part of this talk. It was very interesting. I like
Okay,
it.
I'm glad you do enjoy it, and
Yes,
nice
yes.
to talk to you online.
Yes.
It's long time,
Yes.
after 10, I don't know, 12 or 10, 12 years ago.
Yes, it's more, it's more than 10 years we worked
Yeah,
together.
yeah. That's very nice from you. Yes, yes.
Yes, 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 yes. So yeah, I logged in so I can really listen to your work and then also to see you. It's been
Thank
a
you,
long
Daphne. But are you still at the ICMPA lab, or are you still are you at
I'm
Stellenbosch?
currently at UWC. I still
Okay, okay.
yes,
Okay,
yes.
nice to meet you online. I hope we can meet soon after all this struggle of pandemic.
Yes, 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 yes. I'm still at UWC. I'm doing my postdoc again here at UWC.
Okay.
Yes, yes.
Okay.
Okay.
I hope you will also give a talk so that we follow and see what you're doing now.
In the near future, Laura.
Okay.
Thank you very
Thank
much.
you.
Thank you.
Thanks.
Okay. Okay, so there is a question in the Q&A. So, and I think that's kind of, I do not understand how the word Newtonian can be connected to the words quantum cosmology. This sounds like a physics oxymoron. You talk of Newtonian quantum cosmology. Please explain further this oxymoron.
I talk about Newtonian quantum cosmology. Let me. But when I refer to Newtonian quantum cosmology, I do have, I think it's my very first paper on the topic. And for who asked the question, I would rather says that, okay, this year it is, I will rather bring the person back to the paper that is on archive. And I think in the paper I explain well. As I said, Newtonian, quantum Newtonian cosmology meet very serious criticism that I've read. But I think it's one way also, it's also accepted. There is community accepting this way of doing. And when I work on that, is about considering a toy. For me, it's like a toy model where I consider a small spherical portion of the universe where I can do Newtonian physics and then perform quantization. And then with this portion, I can reflect the evolution of the universe. But these are toy models that so far sometimes not realistic, but also good looking into wise model. And I would, I don't know who asked the question, but I think if the person can take reference of my article on archive, then you will see how things are, how I do my considerations. I know, of course, that is not accepted by everybody, but I see it as a toy model, and I see it as possible also looking in that way to do, to consider Newtonian theory and to do quantization and to solve Schrodinger equation. This was the point.
Okay, okay. So, but I mean, this means that you just consider kind of non-relativistic theory, which you quantize, yes?
Yeah.
Okay, okay. So Newtonian here kind of implies non-relativistic in sense.
Yeah, because you have to see that like a kind of toy model, not always realistic, but that works. If one wants to see, one has to look at things in that way. And then later, I know that if I want to evolve in quantum cosmology, at a certain point, I have to consider Einstein theories. But for the moment, I am happy discussing, checking on Newtonian way of doing. And in fact, I received, I think, a message from a professor in University of Alberta in Canada with certain aspect to look at considering the Newtonian framework. I haven't done that yet, but I mean, the next thing I will do with that is to check, to consider, they have a way of doing, I have to see that. But I know that quantum cosmology, it wins more the Einstein equation stuff that are quite difficult.
Okay, thank you. There is one more question in Q&A.
Yes.
Can you please explain the importance of studying quantization?
The importance of studying quantization?
Yes.
Yeah, I mean, the analogy between classical mechanics and the quantum mechanics as Josta is worth studying quantization as a procedure that they said. It makes sense because there is classical mechanics, there is quantum mechanics. As I said, quantum mechanics is more mathematical build-up of quantum physics, and quantum mechanics comes from the fact that there is classical mechanics, and it's worth that we look into quantization, that is this procedure that link quantum classical mechanics and quantum mechanics. Does make sense. And there are many other quantization procedures that I didn't mention, since the talk is not really about quantization procedures. Also, there are geometrical, there are good reviews about quantization techniques, and it makes sense to study quantizations.
Okay, thank you. So there is no more questions, so back to Francesco.
Yeah, then if there are no more pressing questions, it's up to me, Laure, to thank you very much on behalf of all the participants. Thank you so much for taking the time to prepare a very interesting talk and to be with us this afternoon. And also thank you very much for allowing us to reconnect and also to establish again.
No, I'm glad, of course, to reconnect.
Yeah, no, and also to establish again stronger links between NITheC and ICTP, which are very important. So that,
and we also hope to see you here soon also.
Yeah, no, let's hope so. As soon as we are vaccinated and SAA flies again.
Yes.
Okay, Laure, then thank you so much.
Thank you.
We will,
and thank you for all, both for the participants, that for their time, and yeah.
No. Thank you for your time and for being with us this afternoon. Thank you very much. And thank you also to all the faithful participants that are with us every week. Please join us again next Monday, because we have another exciting talk lined up.
Yeah, from now I will be following, because I follow your talk last week.
Okay.
And from the remote past, I think I follow also a talk, certain talks.
Okay, fantastic. Then if you are on our mailing list, you will receive.
I'm on the mailing list now, so I can follow better.
You're welcome to join us anytime. Yeah.
Thanks.
Thank you very much.
Thank you very much.
So,
bye-bye.
Everyone, have a good evening and take care.
Thanks.
Thank you. Bye-bye.